Hi, everybody. Good afternoon. I'm going to present the work done by Yifang from Oak Ridge National Laboratory. Unfortunately, she couldn't come. But we are a team of researchers at Oak Ridge National Lab funded by the Department of Energy of the US. So I will acknowledge their financial support for this. And today I'm going to talk about a cable-driven parallel robot platform that we are developing. And in particular, we're going to talk about the very beginning studies that we have been conducting in order to analyze the feasible workspace of this type of machines. So the Department of Energy right now is investing in building envelope retrofits because buildings contribute to a large carbon footprint. Most of the buildings in the US are old, so they're not very efficient. And the building envelope, the energy that goes into warm up a house can escape through these inefficient walls. So right now, the system that we're working on is using the pre-manufactured panels in order to install these panels around the house and make the house more efficient. So we are trying to optimize this panelized envelope retrofit as much as we can. Of course, there are plenty of manual installation processes using scaffolding or cranes, but these processes, they take time, they are not precise, and they could endanger the workers depending on the weight of the panels. Robotic installation has been done in the Festus project, so it's good that Technali is around here. So they have developed, and we know that these type of systems are feasible. So inspired on this, we want to push the boundary of how much this can be deployed. So our main deployment idea is these cable-driven parallel robots in urban dense areas. So we want to operate these robots in a very constrained space where you have multifamily residential buildings aligned next to each other. So you are constrained on width and height on the size of the building, and you are constrained on the depth as on the sidewalk size. So you can see there a distribution of sidewalk size in New York City. So we have to work among those constraints. We do not want to exceed the size of that. So then the problem becomes, given these constraints, how you can cover the entire facade with these panels. And cable-driven parallel robots offer a solution for this. First of all, they can handle the panel in a 6 degrees of freedom space. I'm going to say how you can install this in any location, what type of issues arise from this. And also they are attractive because they are simple and compact. But the problem is that the first problem that we're looking here in this research is how to optimize this robot or the design of the robot in order to cover as much space as you can. That is the research question here. So just a little bit on the basics of cable-driven parallel robots. If you look at the static problem, basically you just have a balance of forces and torques. So that is the first equation, is balance of forces. The second is balance of torques. So you want that to be zero, to be static. And you have a constraint equation on force because you have to have a minimum tensile force in order to have a straight cable, and you do not want to exceed the maximum tensile breaking force of the cable. So if you solve that constraint problem, then you obtain the feasible workspace. So all the possible positions where you achieve static equilibrium and you are in the force constraints. So this is an example. This is the easiest robot that you can collect. Just connecting all the edges to the edges of the frame. So here is the panel connected to the frame of the robot. You run those equations in all the points. Basically, right now we're tracking the centroid. So the centroid should be in this yellow space over here. But now you look at where that is feasible. So the green one shows you the feasible locations. The red one shows you the locations that are not feasible. So you cannot reach all possible scenarios. I stole that image from the Hephaestus paper that was published in IARC, so you can see that this is typical, right? So you cannot reach every single corner. So what options are there? Well, the first thing that you could try is study how you can attach the cables to the panel or the carrier. So in a 2D space, you have 24 possible combinations. Out of the 24, really the 4 ones highlighted in the center are really the best. Out of those, if you're in the planar case, really this one is the one that's going to work. In these two, you have issues of cable to cable collision, and this one is really not feasible because you cannot block the panel that you're going to install with cables. Even though this one, as you can see, gives you the maximum coverage, you can cover 100%. So a 2D cable-driven parallel robot is hard to optimize in this space. So we went to the 3D case. In the 3D, we have 8 factorial. So it has so many more combinations of cables. But surprisingly, most of them were infeasible. This is a histogram of all of the ones that achieve over 50% coverage. There is one that is excellent at covering almost most of the facade. However, if you see in the diagram, all the red lines are all the cables that are basically in front of the carrier. And that is not allowable because you want to install a panel. So you don't want to have cables in front of the panel, otherwise you cannot install it. So we analyzed the ones with all those cable collisions and cables constraints, and really 4 of them were attractive, which are the 4 models on the slide. So then we computed the Workspace feasibility. Model number 1 is, again, a very intuitive model where you connect the edges or the corners one-to-one. And the other ones have different interesting connections. But then you can see that some of them work very well on one dimension, but not on the other. So for example, model 2 and 3 are very good at covering the height dimension, but they cannot cover the sides. Model 4 is very good at covering the sides, but it cannot cover the top and the bottom. So one alternative now that we have explored the possible cable combinations was, okay, if you could extend the frame, so if you have to make the frame bigger, then what is the preferable dimension and by how much you have to extend it in order to cover what you need to cover? So these plots here show how much of an extension you can gain, or how much of a coverage you can gain by extending the frame. In particular, for example, for model 4, if you do a 10% extension of the frame, then you can cover almost all of the top part of the building, except the bottom part. Another option that right now we're considering is if you really want to automate the entire process, maybe you need combinations of model 3 and 4, for example, in order to cover the whole thing. So there will be a point in which you have to reattach the connections, the cable connections, in order to achieve it. Or you could just install the first floor manually and then let the top floors installed by the robot. So in conclusions, right now we are trying to develop our own expertise in these cable-driven parallel robots for panelized envelope retrofits. We are very interested in maximizing the capability of these robots, so we are constraining ourselves to these highly dense urban scenarios. We're building a 1/3 scale prototype at Oak Ridge National Lab in order to have a demonstration of this. And as I said, this first study is looking at what you can do to the robot in order to cover as much area as you can. And the 2 things that came up were how you attach your cables have a good impact on it. And then you could extend your frame, given the robot mode that you have, you could either have a width extension or a height extension. and then increase your workspace coverage. So with that, I will open for the panel question, and you can contact Yifang. She's the main author. You can also contact me. We'll be happy to answer any questions you may have.